In the last video, I talked about the correlation between features. So the features which are highly correlated, we do not actually need all of them. We need either of them. So this part of the code deals with removing the highly correlated features. This wasn't implemented in the reference code. I implemented it myself. So this would remove the features which are highly correlated, and to see what features are highly correlated, we print them. This is perimeter mean, perimeter SE, area SE, radius worst, perimeter worst, area worst. This part defines the classes and the attributes. Y defines the the malignant and the benign values. Label encoder basically converts the values of M to 1 and benign to 0, B to 0. Here I've implemented the k-fold cross-validation, stratified k-fold cross-validation to divide to ensure that each set of iteration has equal number of classes of benign and malignant. So we divide the data set here into training and test data set. Then we apply the 6 models that we discussed. First is the logistic regression, and then we train the model here using the fit function. Then we predict on the test data set, and we append the accuracies in the training and the test so that we average out the accuracies of all the iterations. So it says that the training average accuracy was 98.5%, while the test average is 97.19%. Here we are testing the KNN algorithm. We have set the neighbors to 5, and the distance factor or the distance function as Minkowski, and we similarly fit the model, predict the values for the test data set. So it says that the training average accuracy is 96.7%, while the test average is 95.6%. SVC, the support vector machine, has different types of kernels. For example, linear. Linear shows the accuracy to be 98.5% for training and 97.18% for test. Then we have kernel SVM, which is the RBF, radial bias function. It shows that the training average accuracy is 98.39% and the test average to be 97.54%. We also check for the SVM polynomial with polynomial degree of 8 here. So the training average is 79.1% and the testing average is 72.9%, which is quite low as compared to the other models that we saw above. We can also test it on sigmoid. It results in 90.3% on the training average, while 90.15% on the test average. Gaussian knife Bayes. It results in training average of 92.26% and the test average of 91.9%. It assumes that the attributes are independent. Then decision tree. So the decision tree calculates the training accuracy to be 100%, while the testing accuracy to be 92.4%. The random forest also predicts the training accuracy close to 100, it's like 99.9%, and the testing average accuracy is 95%. This plot shows the training and the test accuracy of all the models, basically a comparison of the accuracies of all the models that we saw above. So the blue curve here represents the training accuracy and the orange one represents the test accuracy. So we see that the training and the test accuracy, the training accuracy of decision tree and random forest are both close to 100%. Let's get back to the slide. So part A of the implementation discussed on the comparison of classifiers, supervised machine learning classifiers, and this chart summarizes the results of part A. So it says that this is the polynomial, SVC polynomial performed the worst, as it showed an accuracy of 79.1 on the training and 72.9 on the testing on the test set. While we can see that logistic regression and SVC RBF performed really well on both the testing data set. So convolutional neural network. Convolutional neural network basically is a set of convolution layers followed by a fully connected layer. So we give an input to the convolution layer, we extract the features of the input using the filters, and this generates a feature map. Post that, we apply a ReLU function, which is a rectified linear unit, and it is done to incorporate non-linearity into the data for model to generate a generate and differentiate between the output. And the next layer is the pooling layer. Pooling is done to actually reduce the dimensionality of the parameters or the number of parameters. So after a set of convolution and the pooling layers, here we have a matrix. We flatten the matrix to a vector so that we have a fully connected, so that we can feed the vector into a fully connected network, and this fully connected network is then outputs the probabilities. These probabilities are actually gained from by applying the softmax or any activation function, which classify the object which classify the image. So I'll briefly discuss about the types of CNN. The types of CNN that have been discussed, that have been implemented in part B are DenseNet 201, VGG16, VGG19, and residual network 50. DenseNet 201, it consists of dense blocks which are connected together, concatenated together, and each layer receives an input from the previous layer. So every layer has the knowledge of the previous layers. VGG16 and 19 are visual geometric group networks, and they are both tested and trained on ImageNet dataset. VGG16 consists of 16 layers of weight, while VGG19 consists of 19 layers of weights with 16 convolution layers, while 16 consists of 13 convolution layers. Residual network, it consists of 50 layers, and but as compared to the other deep learning neural networks, it overcomes the problem of degrading the gradient from deeper models. It does this via shortcut connections. It basically connects the input to the xth layer to the input from the xth layer to the x plus nth layer, basically using the shortcut connections. It helps in solving the degrading gradient problem. The next part, the implementation part of this project would be discussed next. So the existing implementation trains and tests the dataset on a single CNN classification model, while the implementation carried out by me is comparison of the 4 models that I discussed previously on the dataset. The implementation part would be discussed in the next video.